Okay, so now that we talked about sensitivity analysis, and maybe you've gone into your building and you've gotten more data, and you've updated your energy model, and now you're ready to compare it to the actual utility data in your building. So this starts a back and forth process called calibration, where you see how well your model matches your data and then figure out what changes you need to make to your model to better match the building. So this is specified in ASHRAE Guideline 14. So you can read that in more detail if you're interested in the specifics. But the two measures of model accuracy that we'll be using, the two statistics, are the coefficient of variation of the root mean square error. So if you've ever taken a statistics class, then you're probably familiar with the mean squared error. And what this statistic says is just how good does my model do at predicting my data. The next statistic that you'll want to look at is the normal mean bias error, which says, does my model tend to over or underestimate the actual energy use? So you'll just take the difference of what you predicted versus what the simulation predicted, and you'll normalize that by the mean of the utility data, and that'll give you a measure for whether you're over or underestimating the energy use. So you'll do this for both electricity and for steam, and if you have chilled water, I'd recommend doing it for that as well. And we'll do this on a monthly basis. So just 12 months. You can do hourly if you really want, but that's not necessary. So the measures to say, okay, my model is calibrated, that we use are if the CV of the root mean square error is less than 15% on a monthly basis or 30% on an hourly basis, and the normal mean bias error is less than 5% on a monthly basis and 10% on an hourly basis. So once you've hit these measures, then we tend to say our model is calibrated. One note I will make about this is that means that your model is matching the utility data of the building. It is possible that there are some parameter that it's just so happens to be the parameter combinations you have, and there is another set of parameter combinations that also describe this. So this is why you'll want to do this on your steam use, electric use, and chilled water if you have it, rather than just total energy use, because you could conceivably come up with a way that you could match the total energy use, but you wouldn't really actually be predicting which end uses in your building, say plug loads versus the heating load, were causing that. So again, be careful with calibration. You sort of have to know what's going on, and if you're getting something like your lighting energy use is 1 kilobTUs per square foot and your plug loads is 80 kilobTUs per square foot and it's still calibrating, well, that's great, but you're probably doing something wrong. So just keep that in mind, and that's sort of an issue with Energy Plus and with these sorts of models which have a whole bunch of input parameters, and you're comparing it to data where you might not have the data you're comparing it to is smaller than the parameter input space, and that's generally an issue called model overfitting, and you can research that more if you're interested. But just be careful of that with your model and try to make sure that what you're actually predicting sort of still matches some benchmarks. So one tool that we do have available, which is in the modeling resources to help with model calibration, and this is from Ryan Mazurk, who helped us out last spring, is a heat map. So what this does is it looks at the electric demand by hour of the day for each day of the year, and the intensity of the color corresponds to the demand. So what's helpful with this is it allows you to pull out some schedules. So in this case, we can see what the HVAC schedules are. We can see at 11 p.m. and at 3 a.m. in this particular building. This is Martin Hall. There is some part of the HVAC system that turns on or turns off. You can also see that at 4 a.m., 5 a.m., and 6 a.m. as well. So that's probably something with some fan setting or something that we could then look back at our model and maybe ask a building manager or something, and we could say, oh, okay, so now I have a more accurate estimate for my HVAC schedule. This variation that we have here, some of that is going to be due to the cooling load and the heating load, and some of that's actually due to occupancy variation over the year. So you can tell when the semesters are, right? This is the winter semester, here's spring break, winter semester. This is summer, so there's less people in the building. And then again, we have the fall semester here. So if you know information about the scheduling of the building, then that can help you a bit more pick out what your actual plug loads should be and what your occupancy should be. And so you can update your model, and then that's sort of a recalibration and compare it and see if it matches. And that's one way to sort of help avoid this sort of model overfitting, is if you know more information about the building, then you can make sure that the parameters that you're changing are probably pretty accurate, that those are the parameters that should be changed. So I hope that this was helpful to you, and it will help you calibrate your building model.